Okay, hello guys, welcome. This is video from section 6.2. Section 6.2 is about one-to-one functions and inverse functions. Okay, so let's start with definition. A function is one-to-one if each input has a unique different output. Okay, so what happened? Okay, that function is one to one. Okay, so technically, how you're going to know that function is one to one? First of all, for equation, graph, relationship, something to be a function, you guys know already that x coordinates can't repeat. So that's the easy way of knowing that something it's a function. If we have one-to-one function, what's going to happen? If you have one-to-one function, also y coordinates can't repeat. So I remember when I teach you guys in the class about functions and explaining the definition, regular function, I told you that you guys and me are a function, okay? Because students are input and a teacher was output. So each student had exactly one teacher for college algebra. However, the function, okay, students and teacher is not one-to-one because for function to be one-to-one, so technically this is how that's supposed to work. Each student supposed to have one unique teacher. So if we have 14 students in a classroom, those 14 students should have 14 different teachers for college algebra. So that's the difference between regular function and one-to-one function. Okay, so again, remember that that still apply that because one-to-one it's a function that x coordinates can repeat, but now we adding that we're dealing with one-to-one function, so also y coordinates can't repeat. So let me give you the examples. Using the graphs. So linear functions. Y equal mx plus b. Okay, linear functions. So the graph of linear function, okay, y equal mx plus b. They are definitely one-to-one. So each input has exactly one output, and that's a unique output. Another example of one-to-one function, y equal x to the third power. So this is cubic function, okay? Okay, let's just review how the graph looks like. So the cubic function, this is how the graph looks like, is also one-to-one. Okay, each x has unique y value. Okay, y coordinates one repeat. However, y equal x squared is not 1 to 1. So let's graph. So any quadratic function is not 1 to 1. I'm going to graph the basic one, y equal x squared. Okay, let's talk about those 2 points, 1 comma 1, and the one which is symmetric with respect to the y-axis, negative 1 comma 1. So based on those 2 points, we have 1 comma 1, negative 1 comma 1. So y equal x squared is definitely quadratic function, so it's a function, but it's not 1 to 1 function because look what happened. They have the same y coordinate. So 1 to 1 function, again, we cannot have that situation that each input, that 2 inputs or more has the same output. Okay, so note y can't repeat. Okay, it has to be unique in 1 to 1 in 1 to 1 function. So the best way, just to again not get complicated, for 1 to 1 function, always make sure that x is unique and y is unique. So x doesn't repeat because that's the definition of the function, and also y can't repeat. Okay, so let's deal with the example 1. And I'm going to use the example from the textbook. We have to decide whether a function is 1 to 1. 1x goes to 1y. Okay, and the example which I'm using, it's from your textbook. This is page 401, 419, number 13. So they give you mapping. Okay, mapping means like you're going to see a map. We have a domain, and the domain are hours of working. So that's our inputs, which means x values. And they give you range. Range is the output. It's going to mean money, okay, how much we make after, let's say, working 20 hours. So here we have 200, 300, 350, 425. Okay, so range, that's the output, y values. And again, you're going to see many problems like that, and they give you mapping. And you have to decide if this relation represents 1 to 1 function, okay? So the answer will be yes. This function is 1 to 1 because each input is mapping with the unique y values. With a unique, different y values. Okay, so when we're working 20 hours, we're getting 200. pay. When you work 40 hours, you're getting 425. So definitely, this is one-to-one function. Okay? So I think one example of mapping it's enough. And I also want to go over another example, which is in your textbook on page 420, number 17. They also asking you to decide whether the function is one-to-one. And they give you different scenario. Right now, they give you the original function, and they listing some of the points from that function, order pairs. So we have 2 comma 6, then we have negative 3 comma 6, 4 comma 9, 1 comma 10. And we have to decide if this function is one-to-one. So of course, first number represents input, which is x, and the second number represents y. Okay, so what you guys think? This is one-to-one. The answer will be no. This function is not one-to-one. And again, for one-to-one function, now we comparing y's. We're checking what happened with y's, and look what happened. There are 2 points which have the same y coordinate, which mapping with the same y values, which can't happen in one-to-one function. Okay, no, again, because 2 different inputs share the same output, which is y value. That can't happen, okay? It's a function, but it's not one-to-one, okay? It has to be one unique x matched with one unique y value. Okay, so that's what you're going to do for homework. Now, next, what we're going to talk about it, I will give you the definition of horizontal line test. So horizontal line test is the test which will tell you to decide from the graph if the given function is one-to-one. So it works exactly the same way like vertical line test. So you're going to draw the horizontal line, and if horizontal line intersect or touch the graph once only, this graph represents one-to-one function. Otherwise, it's not one-to-one. So let me just write this down. So horizontal line test, okay, help to decide from the graph if the given function is one-to-one. And this is how it works. So if horizontal line, again, imagine a horizontal line. If horizontal line intersect or touch, okay, the graph of the function once only, that means that this function is 1 to 1. Otherwise, it's not 1 to 1. Okay, so let's do a couple examples with horizontal line test. And the best way to practice that will be also the problems from your textbook, page 420. And we will solve problems 21 through 26. Okay, so 21 through 26, they give you graphs. Okay, and we just need to decide if we have one-to-one function. 22, that's the graph. 23, we have absolute value function. Then 24, they gave you quadratic function. Twenty-five, and 26. 26, they give you the horizontal line. And in those problems, again, you have to decide which graph represents one-to-one function. Okay, so let's check what you guys going to do. So I'm doing the horizontal line test. I'm drawing the horizontal line. Okay, since my horizontal line intersect graph once only, so yes, this is one-to-one. In number 22, I'm doing the same thing. I'm drawing horizontal line. It doesn't matter where you draw. This is your test. And my horizontal line intersect graph once only, so the same answer, yes, one-to-one. The graph 23, this is absolute value function. I'm drawing horizontal line. Since my horizontal graph line touch the graph twice, intersect graph twice, so this is no, not one-to-one. Okay, so the answer is no here. For 24, I'm drawing the horizontal line. Since my horizontal line intersect the graph of the function twice, so the answer is no, not one-to-one. And 25, we draw the horizontal line. Horizontal line intersect graph once only, so yes, this graph is one-to-one. And 26, your graph is horizontal line. Okay, so that was the graph of the function. So if I would draw the horizontal line, so my horizontal line will overlap with original graph, which means horizontal line touch my graph in infinitely many points, so definitely not. No, not one-to-one. Okay, so this is how you're using horizontal line test. Okay, I think it's a very nice and useful test to quickly check if your graph is one-to-one. Okay, next what we're going to do, I'm going to explain the theorem. It's a very useful tune. Um, a function which is only increasing or decreasing in entire interval, those functions will always be one to one. Okay, so let me just write this down and I will explain based on the examples which we just did. A function that is increasing on interval I, so again, depends of the problem, is one to one. Function on interval I. And the same thing with decreasing. A function that is decreasing on interval I is one to one. On interval I. So what that means, if you guys have one-to-one function, like the first one, so how are you going to also know that your function is one-to-one? If your function is either only increasing, like example 21, okay, like you see our graph, it's increasing. There's no change from increasing to decreasing. This function definitely will be one-to-one on the interval. In this case, it's increasing from negative infinity to positive infinity. Since we don't have that change from increasing, decreasing, this one has to be one-to-one. So one-to-one functions don't have local minimums and local maximums. The same thing, this graph. Okay, let's go back to 25. Graph 25, this function right here, it's decreasing. Okay, so this graph decrease. It decreased from 0 to positive infinity. So since this function it's decreasing in the entire domain, which is from 0 to positive infinity, it has to be one-to-one. Like you see, there is no local minimum, no local maximum, because we don't have that change from increasing to decreasing. Okay. 24, just quickly going back to 24, okay? Look on 24, your graph, okay? This is quadratic function, okay? Here, look what happened. This quadratic function increase, and there is a change at point, at vertex, from increasing to decreasing. So when your graph change behavior, when your function change behavior from increasing to decreasing, decreasing to increasing, it will never be one-to-one. So that's what the definition explains. So note. And this is really important, okay? One-to-one functions, okay, don't have local maximum or local minimum. They either increase or decrease on entire domain. In entire, we don't have that change of behavior. Okay. Okay. Another important note about one-to-one. Okay. for all one-to-one functions, you can always find the inverse function. Okay? So all one-to-one functions have inverse function. Okay, so that's it from the information. Okay, of course we'll continue. Now, since we talk about inverse functions, we're going to review how to find inverse functions. So I'm going to write the steps how to find the inverse functions in a second. So let's just start with the example. Let's move on a little bit to inverse functions of one-to-one. Here, starting from now, we're going to focus on finding inverse of function. We're going to do a couple examples. First, defined by a map. Okay, couple of notes before we move on. So let's just review that inverse function. So if function f of x, which is your original function, is a set of ordered pairs x comma y, then the inverse function of f of x is defined. So again, inverse function f, it looks like to the power of -1 of x, this is the notation of inverse function, is the set of ordered pairs and again, what happened with inverse function, what used to be x will become y, and what used to be y will become x. Okay, so we switching the order of coordinates. Okay, let's review that. I know we talk about inverse function, but just in case if you need the review, domain of f of x, which is original function, it's always going to be equal to range of the inverse function. And range of original function, it's always going to be the domain of inverse function. Okay. And now we're ready to move on to example. Okay, this is from page 420, example 27, exercise 27. So they want you to find the inverse of one-to-one function. So we already know that given function is one-to-one function. And you need to state the domain and the range. Of the inverse. So first, this is the example when they give you mapping. So that's the nice example. We have location. That's our domain of original function. So this is again a situation of original function. They give us Atlanta, Boston, Las Vegas, Miami, Los Angeles. So, and the second map represents annual precipitation in inches. Okay, so how much rain we getting? Okay, in each of those towns. So 49.7, 43.8, 4.2, 61.9, and then 12.8. So we have domain and range. This is the mapping. Definitely this example represents one-to-one function. Each input has unique output. Okay, so what they want you to do, they want you to find the inverse function. So this is again, this situation represents f of x. That's our original function. So to find the inverse function, okay, so inverse function, what's going to happen? What used to be domain, range will become domain. So right now, the domain of inverse function will be annual precipitation. Okay, so 49.7, 43.8, 4.2, 61.9, 12.8. Okay, and the range of inverse function, it's the domain of original function, which means location. Okay, so we have Atlanta, Boston, Las Vegas, Miami, and Los Angeles. So this function is one-to-one function. Like you see, the range of original function become domain of inverse function. So this is again when you guys will be working on my MATLAB of those problems. Of course, you just will have to select the correct one. Now, next, they asking you to state the domain and the range of inverse. So, domain of inverse function is annual precipitation. So I will just list those numbers: 49.7, 43.8, 4.2, 61.9, 12.8. And the range of the inverse, that's going to be location. So I'm going to list location, just Atlanta, Boston, Las Vegas, Miami, Los Angeles. Okay. Okay, So that's what you will need to do with the problems like that. And again, like you guys see, we going back because we deal with one inverse functions. Here we adding that we dealing with inverses of one-to-one functions. And you will have exactly the same problem, I mean similar problem, but they will give you from order pairs. Okay, so this is example from page 420, number 31. So I'm not going to copy this down, but they asking you also to find the inverse of one-to-one function, state the domain and range of inverse function. So the same, they asking for the same thing, okay? However, different scenario. So in this case, they give you original function, f of x, as a set of order pairs. So we have -3 comma 5, -2 comma 9, -1.2, -1 comma 2, 0, 11, 1, -5, and you have to find inverse function. So inverse function, we're switching x with y. So it's going to be 5 comma -3, 9 comma -2, 2 comma -1, 11 comma 0, -5 comma 1. So that's the inverse function. So you have to create the inverse function and then decide what is the domain of the inverse. Okay, so domain of the inverse, you're going to list the x coordinates of each order pair. So it's going to be 5, 9, 2, 11, -5. I don't think my MATLAB will ask you to put them in order. Range of inverse, just list the y coordinates. So it's -3, -2, -1, 0, 1. Okay. Okay, I think that's enough from those type of problems. More theorems. So let's just move on. So we have theorem. Okay. If f of x is one-to-one function, then composition f composed with inverse, it's equal x, and inverse composed with original function always give you x. So again, f composed with inverse, that means f composed with the inverse. Maybe this is better to write that way. Inverse function composed with original function, and we always getting x. Very important, okay? So the composition of inverse and original function, and it only works for function which are one-to-one, will always give you x. So again, if function is one-to-one, that's super important because we did the composition, we didn't get x before last week. But if function's one-to-one, always composition of the function with its inverse is always equal to x, okay? And later we'll see on the graph what that x represents. Technically, why this is always equal x, because original function, which is one-to-one, and her inverse, if you graph it together, those graphs will be symmetric with respect to the line y equal x, okay, which we call identity function. So that's why you have that. Okay, it comes from actually from graphing. Inverse function and original function, if they are one to one, they always will be symmetric with respect to the y equal x. So I will write this down later, but here we're going to focus on verifying inverse functions. So it's a lot of review, okay, in this section. So I'm going to your textbook. This is page, again, 420, and I'm going to explain what we're going to do based on using of example 35, exercise 35. They will ask you to verify that functions f and g are inverses of each other by showing, technically using the theorem which I just gave you, by showing that f composed with g of x it's equal x, and g composed with f of x also will give you x. So this is what we need to show. Okay. And then I'm going to copy everything what they asking you. Okay, so then it will make sense. Given, not given, give any values of x that need to excluded from the domain of f and domain of g. So technically they're asking you to verify what is the domain of function f and what is the domain of function g. Okay, so this is what they give you. They give you the equation function f of x, which is equal 3x plus 4. This is equation function g of x, which is equal 1/3 times x minus 4. First, I'm just going to quickly talk about domains. So function f of x, it's a linear function. So domain of linear function is all real, which means from negative infinity to infinity. So we don't need to exclude any values. For g of x, technically, if you will distribute 1/3, you're also getting the function in form y is equal mx plus b, slope intercept form. This is linear. So domain of g of x is all real numbers, which means from negative infinity to infinity. So we don't need to worry about excluding any x values because domain is all real. So now we need to show that f of x and g of x are inverses of each other. Okay, how are we going to do it? By showing, by the theorem, if functions one to one, which all linear functions are one to one, a function composed with its inverse always will give you x. So this is what we need to prove. So first, we need to show that f composed with g of x is equal x. So let's create that composition, f composed with g of x. F composed with g of x. Okay, so f and g of x has equation 1/3 times x minus 4. Okay, so what we're going to do, you're going to copy the equation of function f, which is outside, which was 3x plus 4. However, where we used to have x, you're going to plug in function g, where we used to have x. So function g has the equation 1/3 times x minus 4. So we will simplify that. 3 times 1/3 will cancel, so we end up with x minus 4 plus 4, which is just x. So we good. So far, the first condition work, that f composed with inverse, which is g, will give you x. Next, what you need to show, that g composed with f also will give you x. So second, show that g composed with f is equal x. So show that inverse of function g is function f of x. So now outside you have function g, inside you have function f of x. Equation of function f of x is 3x plus 4. Excuse me. So what we're going to do, g is outside, copy the equation of outside function, which is 1/3 times x minus 4. And where you used to have x, you plug in function f, which has the equation 3x plus 4. Hold on. G, 1/3 times x minus 4, and f of x is 3x plus 4. So g composed with f. G, 3x plus 4. Okay. 1/3 x minus 4. Okay, let's simplify. So we're getting 1/3 times, remember about order of operations. So first you're going to simplify the parentheses. So you're going to end up with 3x only because 4 and negative 4 cancel. And now we have 1/3 times 3x. That will cancel, and this is equal to x. So we just prove it. Next, I'm going to stop here because this video has already 45 minutes and I have a couple more examples. So video section 6.2 will have 2 videos. So this is video 1. Okay, and I will post the second video, which won't be such a long one.